All right, so this section of notes is going to deal with the electrical conduction system of the heart. This is where we're going to end up looking at an EKG or an ECG tracing, an electrocardiogram. This is covered starting on page 376, I think, in your textbook. The explanation in there obviously is going to go into more detail than what you see here, and it's not broken down this way, so I would definitely look at that maybe in conjunction with these notes. So to just start though, cardiac muscle is said to be self-excitatory, which just basically means it's not under control of the nervous system, that it generates its own action potentials in order to contract. So we're going to start with those action potentials being generated at the sinoatrial or the SA node. That's in the right atrium. It's going to initiate those impulses at a rate of about 70 to 80 per minute, okay, beats per minute. And those impulses are going to enter the atria, and then that's going to cause the atria to contract. And then from the SA node, it's going to travel, the conduction system is going to travel to the AV, or the atrioventricular node, and this is at the junction of the right atrium and ventricle. It's going to slow down the impulses a little bit, and that's going to allow for the atria to finish contracting and for the ventricles to fill with blood, okay? And so then from there, now the ventricles are full. Essentially, the electrical conduction system is going to travel to the AV bundle, which is also known as the bundle of His. And this is at the top part or the superior portion of the IV or interventricular septum. So the impulses are going to go through the AV bundle until it's going to split to form what are known as the bundle branches. And they're about halfway down the IV septum. They're going to enlarge and they're going to turn into what are known as Purkinje fibers. And so then it says impulses travel through both of those bundle branches, okay, and then back up through the walls of the ventricles. When they're going back, those impulses are going back up the ventricular walls. They're going to cause the ventricles to contract, and as they go up the walls, that's when it's moving through the Purkinje fibers. Okay, so to look at this picture in conjunction with the last slide. So again, we're going to start with electrical conduction beginning at the SA node that's self-excitatory. Okay, the impulses are going to first travel to the AV node that's here. Those impulses are going to slow down a little bit there just to let the ventricles fill with blood and the atria finish contracting and essentially being empty of blood. From there, this impulse is going to go into the AV bundle or the bundle of His, down these left and right bundle branches that are going to turn into Purkinje fibers. And then as you see the impulse going up the sides of the ventricles, that's when the ventricles are contracting as that impulse is going through the Purkinje fibers. And this is all happening, if we go back to nervous system content from last semester, it's all happening when these muscle cells are depolarizing and then repolarizing. Okay, so I definitely suggest that you go back to your nervous system notes and look at nerve impulse conduction. Okay, so remember that when a neuron's polarized and it's resting, right, that when a stimulus causes that neuron to fire, that sodium is going to be what moves from the outside of the membrane to the inside of the membrane of the cell, and the cell's going to become more positive. So that's depolarization. And then for a quick recap of repolarization, just basically almost at the same time, okay, once the sodium starts to flow in, the potassium is going to flow out of the cell, right? So now there's going to be more positive ions in the form of potassium on the outside than there were on the inside, and then that's going to cause the inside of the cell to be more negatively charged again. Remember, we're dealing with all positive ions as far as that goes. So these changes in polarity, again, are going to be really important to understand for this unit with depolarization and repolarization of the heart muscle. So then when we look at this diagram, there's really three main things we're focusing on here, but to see this broken down with some of these other steps, okay, and looking at the cardiac conduction system may help you to have a better understanding of what's going on. So we're most concerned with the P wave, the QRS complex, and the T wave, okay? And then here, just as not a recap, but just to kind of tie this to depolarization and repolarization. So right before or causing the production of a contraction, that's when depolarization is going to take place, okay? So sodium moving in. And then when repolarization takes place, that's right before, or that's causing a relaxation event. So that's when the potassium is going to leave the cell. right? So if we notice here, first the P wave, that's when the atria are contracting. You've got the sinoatrial node involved there as far as initiating those impulses, okay? And then the atria are going to contract. I'll let you kind of walk yourself through what the H and everything else that's right there means. And then we get to here, okay, in the QRS complex, right? We're going to be concerned with that. And I'm going to show you a couple things on a different slide in just a second. And then we get to the T wave, and we're concerned with that. Let me go to the other one. All right, so I switched to this one because even though it's yellow on gray, it's a little bit easier to see as far as just the size of the words. So again, sinoatrial nodes essentially acting right here, okay? And so this P wave, this is depolarization of the atria before they're contracting, right? And then when we get to the QRS complex, notice that that's depolarization of the ventricles, and that's preceding the ventricles contracting, right? Notice there too that it says it hides the repolarization of the atria, that event is happening at the same time that the ventricles are depolarizing. So as the atria relax, the ventricles are contracting. So in all reality, the peak of this QRS complex is really much larger than what we see here, but its height is negated by this repolarization event. Okay, if that was not happening at the same time, this ventricular contraction would produce a much higher peak on the graph. Then we get to repolarization of the ventricles. That's marked by the T wave. Okay, so then if you look at this, you basically read left to right and top to bottom on here, okay? Tying what you see in yellow, so blood in the heart. Okay, SA node is under action as far as initiating an impulse, okay? And then we start to see the P wave forming. The P wave formed here. This is the atria contracting, right? And as they contract, right, starts to push blood down into the ventricles as far as the valves being open there, right? We see the entire P wave at that point, okay? And then here, we've got more blood in the ventricles, right? We see the formation of the QRS complex. We see the whole QRS complex over here. And this is showing that the atria have completely contracted, okay? And so that there's no blood as far as this particular round of contraction being shown here in the atria. It's all here in the ventricles, okay? Now, granted, at the same time, this is happening over again, okay? And so then here, we've got ventricular contraction being shown. That impulse is going to travel through the Purkinje fibers up the walls of the ventricles, okay, and then we're going to see ventricular relaxation appear with the T wave, okay. Hang on. All right, and so then again here, just a really simplistic cardiac cycle, okay, depolarization and contraction of the atria, ventricular depolarization, so they're going to contract, and then ventricular repolarization where those are going to relax. For a couple things on here. So first off, just to go ahead and mention that when somebody has a fast heartbeat, it's just tachycardia to keep it simple for us. When it's slow, it's bradycardia. Up top, this normal heartbeat, I marked off several cardiac cycles. Okay, so these are just heartbeats, okay, as far as what you want to count. So if we start here, because that's the beginning of a P wave, we would count 1, 2, 3, 4, 5 complete cardiac cycles there. On here, because you can't really see the beginning of a P wave, I left that one off. It's pretty close to being complete, okay? But just to start here, from the beginning of a P wave to the beginning of the next one, okay? So that's 1. Here's another one. That's 2, okay? And then this one, of course, is irregular. We're not going to talk about that right now. Okay, and just real quick for a quick physics lesson, when you look at wavelengths in physics, on a wave, you measure, so this is just a one wave, this is another set of waves. You measure from the same point on one wave to the next to get a wavelength. Okay, so that would be basically you could measure 3 different wavelengths there and look at their distance here. Okay, that's a much longer wavelength than it is here. You can look at the height of waves as well. You also, in the grand scheme of things, so I just picked that point on those waves. You can measure a wavelength from here to here, also from here to here. We could look at the trough here to here, okay, the peak of the wave from here to here. So you go from one point on one wave to the exact same point on the next wave to measure a wavelength. That's why it's easy to do this on this normal heartbeat here, and then it's easy to see on this fast one because it's at least the same consistent slowness on there. It's harder to determine a true wavelength across a pattern when you have an irregular heartbeat. All right, so then just real quick, this is just a picture that's in your textbook on 378. So we will eventually read these and calculate heart rate in 3 different ways, and hopefully get to do a lab dealing with EKGs or ECGs, electrocardiograms, where we look at essentially how many cardiac cycles are happening on a tracing. So this is just showing like from the beginning of one P wave to the beginning of another one, but we will then look at, I'm going to slide this over, okay, this is just showing a couple of different, there's really A through I on here, but just to show you a couple of different things that we will not get into a ton, but how these just EKG tracings do not always look normal. And so we're going to attempt to do a lab with this, assuming that we've got time. Let me know if you have any questions.